So, in the previous video, we went over how to find vertical asymptotes of rational functions. But we know that there's also this term of a horizontal asymptote, and even at the very beginning, something called an oblique asymptote, which I mentioned was also called a slant asymptote. Oblique really is the better term, but anyway. So, the horizontal asymptote is the end behavior. So here's how you find the end behavior of a rational function. Suppose I have a polynomial over a polynomial. This is of degree n, and the denominator is of degree m. So they've already been written in their sort of standard form. If the numerator has a bigger degree than the denominator, sorry, smaller. I misread the symbol. If the numerator has a smaller degree than the denominator, then y equals 0 is a horizontal asymptote. It's fairly straightforward. If the power on top is smaller than the power on the bottom, and when I say the power, I mean the largest power. The largest power on top is smaller than the largest power on bottom. Horizontal line, y equals 0, there's your horizontal asymptote. If, however, the two highest powers are the same, for example, I have 12x to the 10th, and then a bunch of other stuff, so I have a degree 10 polynomial, over 6x to the 10th, and then a bunch of stuff. The 12 and the 6 being different is fine. It's the x to the 10th being the same. The degrees are the same. Then you take that ratio of the two coefficients, and there's a horizontal asymptote. Okay. If the degree on top is exactly one larger than the degree on bottom, there's going to be a line, which is called a slant or oblique asymptote, and you're going to find what line it is using this scary thing, polynomial division, polynomial long division. Okay, so in summary, if the degree on top is smaller, y equals 0 is your horizontal asymptote. If the degree on top is equal, y equals the ratio of the leading coefficients is your horizontal asymptote. And if the degree on top is one larger, you do polynomial long division to find a line that is your oblique or slant asymptote. If the degree on top is bigger than that, at least 2 over, the end behavior represents a certain power function, which you would determine using polynomial long division. Okay. So let's see some examples. Set aside the problem of vertical asymptotes. That was the last slide, the last video. Okay. Eventually, you'll have to do both, but for now, just find horizontal asymptotes. So what you should ask is, what's the degree of the numerator? What's the degree of the denominator? Which is bigger, or are they equal? And then follow the steps on the previous slides. So the degree of the numerator is 4. The degree of the denominator is 6. The degree on top is less than the degree on bottom, which means y equals 0 is a horizontal asymptote. It's actually the only horizontal asymptote. How about this one right here? Well, the degree of the top of the numerator is 1 larger. It's of degree 3 compared to degree 2. So it has an oblique asymptote, and we have to do polynomial division. Okay. I kind of wish the slide didn't immediately jump to the answer. See, we have to do division. We have x squared plus x plus 1 into 2x cubed plus 3x squared plus 0x plus 2. Remember, if you're missing some powers of x, like this doesn't have an x to the first in it, put it in there with a 0. Now we're just doing the division algorithm. And really all you have to do is play the largest powers against one another. So my biggest power of my divisor is x squared. And I'm trying to put it into 2x cubed. So I'm missing a 2 and I'm missing an x. Now I do this multiplication. 2x times that divisor gives me 2x cubed. It also gives me 2x squared. It gives me 2x. And then I'm going to subtract all of that. The 2x cubed minus 2x cubed cancels off, and that was the point. Okay? Your biggest term should always cancel if you've done this correctly. 3x squared minus 2x squared gives me x squared. 0 minus 2x gives me minus 2x. And then I'll bring down this 2. Well, then play the big power against one another. What does x squared have to get multiplied by in order to end up with x squared? A 1. Then I would have x squared plus x plus 1. I'd subtract it, and I'd end up with negative 3x plus 1. And now this power 2 is smaller than this power 1, so I have my remainder. Okay, so this is 2x plus 1 with a remainder of negative 3x plus 1 over the divisor. So this is what happens when you do the long division. Okay. But now let's see what this kind of says. Look at that remainder term. So this remainder term is a rational function all on its own. But it's now a rational function where the degree of the denominator is bigger than the degree of the numerator. If you've done your long division properly, this is what will happen. Once you do the long division, we now have a smaller degree over a larger degree. So this goes to 0 as x goes to infinity. It has this bit by its own, has a horizontal asymptote of y equals 0, because the degree on top was smaller and the degree on bottom was bigger. So the highlighted piece on its own has horizontal asymptote y equals 0, which means when x is really, really big, the highlighted bit is very close to 0. Which means as x is really big, h of x is really kind of just 2x plus 1. It's 2x plus 1 plus something very, very small as x is very big. If x is very big, highlighted bit goes to 0, so you ignore it, which means if x is big, this function just looks like 2x plus 1. And that's what this long division tells you. Okay? That as x goes to infinity, this is going to go to 0, which means this bit here is really what's controlling the function. So this remainder term goes to 0. So all we have left is the 2x plus 1, and that's what a slant asymptote is. Okay. So they didn't graph it, which is too bad. If you graph this, here's the line 2x plus 1. Okay. This denominator does not have any real roots. If you apply the quadratic formula to this denominator, you'll see that there are no real roots. So there actually are not any, vertical asymptotes. So what this graph ends up looking like is something like this, I think. Basically, as x goes to infinity, you sort of squeeze down on this line. Just like a horizontal asymptote will be something like as x goes to infinity, you squeeze down on a horizontal line. A slant asymptote is as x goes to infinity, you squeeze down on a slant line. So let's do another example, all the same steps. Find the horizontal or slant asymptote, if it exists, of the following. First step, make sure it's in lowest terms. Then ask what's the degree of the numerator versus the degree of the denominator, and go through those steps. So it is in lowest. The degree of the numerator and denominator are both 2, which means you just have to take the ratio of leading coefficients, which is just 9 over 3, and you get y equals 3 is a horizontal asymptote. And the reasoning is pretty similar. Okay, as x gets bigger and bigger and bigger, the x squared is way more important than the x or the 1. And as x gets bigger and bigger in the denominator, the 2 is fundamentally not so important. So as x gets really, really huge, the x, the 1, and the 2 are much, much smaller than either the 9x squared or the 3x. And now I can cancel off the x squareds, and I just get 9 over 3. That's the reasoning behind this process. And this is what I just said. If you want to read it in different words the way the book puts it, go ahead and pause and just slide. It's exactly what I just read through on the previous one. OK. So the graph of the rational function has a horizontal asymptote of y equals 3. That just means as x goes off to infinity, it looks closer and closer to y equals 3. It's going to squeeze down on it. OK, another example. Same question. Here's a rational function. Find the horizontal or oblique asymptote if one exists. So again, check the powers, the degrees of the numerator and denominator. Well, in this case, it's 2 larger, which means it does not have a horizontal asymptote. It also doesn't have a slant asymptote. Okay? The end behavior of the graph is going to look kind of like, well, the numerator looks fundamentally like 10x to the 5th. Once x is enormous, the cubing and the square and the constant 2 are not so important. And in the denominator, the -1 is not nearly as important as the x cubed. So as x is very, very big, going to look very much like 10x to the 5th over x cubed, which is just 10x squared. Okay, so there's that. If the degree of the numerator is smaller than the degree of the denominator, y equals 0 is your horizontal asymptote. If they are equal, you take the ratio of leading coefficients. If the degree of the numerator is 1 larger than the degree of the denominator, then you do polynomial long division to find a slant asymptote. If the degree of the numerator is 2 or more larger than the degree of the denominator, it doesn't have a slant or horizontal asymptote, but you can still find a power function that sort of predicts the behavior of the graph. All right, so that's the end of section 4.3, I want to say. I'm starting to lose track. I'm pretty sure that was 4.3.